Okay, so this next lesson is pertaining to the normal probability distribution and how to calculate probabilities associated with it along different intervals. Okay, so let's start off by getting into what is the normal probability distribution and why does the normal probability distribution even matter? Okay, let's back up for a second and say, what is a probability distribution? A probability distribution is the combination of all the potential values a variable can take on and the relative likelihood of that value occurring. In other words, it's everything that could happen and how likely it is, or the odds that it could happen. Okay, so when it comes to probability distributions, if probability distributions are really just the centerpiece of quantitative analysis, and there's nothing to a probability distribution other than it's everything that can happen and the likelihood of that thing happening. That basically tells us that there are an infinite number of probability distributions that exist in the world. And this is true. There's an infinite number of probability distributions. They come into existence and go out of existence all the time. Right now, at this very moment, there are millions of probability distributions that are being born, and then there are millions of probability distributions that are going away right now. And for example, as we are speaking, right, as I'm speaking to you, right, recording this, my heart is beating. And every time my heart beats, there is a specific probability distribution associated with the strength that it is going to pulse with, right? That it's actually going to beat. There is a specific strength associated with that and a likelihood of that occurring. So, boop, boop, there it goes, right? And boop, boop, there it goes again. Okay. And as soon as that heart beats, that probability distribution is gone and we're on to the next one. And then there's a probability distribution of my heart beating with this amount of strength or that amount of strength or this excess strength or not enough strength and the likelihood of that happening. And then boop, boop, and then on to the next one. So there are millions and millions of probability distributions that come into existence and then go out of existence every single second. Okay. There's an infinite number of probability distributions that exist in the world. So if I was to ask you, what is the probability that IBM stock finishes the day between 140 and $160? You might say to yourself, well, I'm not sure. I mean, there's, an infinite number of probability distributions out there. I'm not particularly knowledgeable yet on how I might go about calculating the odds of that happening, and that's okay. But what I want to stress to you is since there's an infinite number of probability distributions out there, sometimes the calculations for, how to get or obtain probability estimates can get rather confusing or messy, or you might think it would get that way. Couldn't be further from the truth. Okay. In point of fact, all quantitative analysis, for the most part, 99.9999% of quantitative analysis comes back and uses something that is known as the normal probability distribution. Okay, that's the one that everybody uses. The same way that, in theory, there's not an infinite number of languages, but in the world, there are thousands, if not tens of thousands of languages that exist all over the globe. Okay. But at the end of the day, when you want some sort of an international translation or something that everyone can more or less relate to, people tend to go back to either English or French, but usually English. Okay. In other words, English is the center of gravity, if you will, when it comes to global communication. Okay. Well, in quantitative analysis, even though there are thousands, if not tens of thousands, if not millions and billions, and if not an infinite number of probability distributions that are out there, right? Out of an infinite number of probability distributions, the center of gravity that everyone comes back to in quantitative analysis, that center of gravity is the normal probability distribution. Okay. In other words, it's what everybody tries to get their analysis into so that it becomes more understandable, more legible. Okay. So let's start off by talking about what is the normal probability distribution. Okay. The normal probability distribution is, let's get to a whiteboard. I'm just waiting for it to load. Okay. The normal probability distribution. Normal probability distribution has the following features. Okay. So just to remind the viewer, it's a probability distribution, right? What's a probability distribution? It's a combination of all potential values a variable can take on and the likelihood of that occurring. Okay. So this is one type of that. And it's one that you're probably familiar with or have heard about before. Okay, the normal probability distribution is that it is bell-shaped. Okay. If you've ever heard of the bell curve, that they're talking about the normal probability distribution. So here we go. The normal probability distribution, right, is shaped like a bell. This is kind of, if you imagine sort of the little handle that you shake up there, ding, 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 right? Ding, ding, ding. You would hold it here, and then the bell would, sort of drop down right in here and ding, 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 ding. That's the normal probability. Okay. So it's bell shaped. Okay. So just to be totally clear, probability distribution, right? We have values on the horizontal axis, and then we have probability. I'm just not drawing it, but we have probability on the vertical axis, right? So this is our probability, and this is our values, okay? So the higher something goes, like right here, the more probable or likely it is to occur. These values are not likely to occur. Okay, these ones in the tails. This is out in the left tail. This is in the right tail. These values are not likely to occur. Their probability is low, right? On the other hand, these values right around the center, the values in the center, it's very high. That's very likely to occur. Okay, why? Because it's up here, right? It's higher up the probability uh, axes. Okay. So just important to remember, right? This line, this bell curve is nothing more than a line that you could draw over all of our individual observations, right? We have all these individual observations, right? This is observation 1, observation 28, observation 44, observation 3, observation 18. All these are all individual elements of our data sets, right? This is an element, this is an individual element, this is an well, if we take all these elements like so, We just erase everything here, right? If we take all these elements and graph them, right? We just draw them out. These values, not very high with let me put the probability axis just so we see it from the beginning, right? So these values, not very likely. These values, not very likely. But these values, very likely. Everything towards the center likely to happen. If you draw a line over that to encapsulate or encompass them, you end up with something that more or less looks like the normal probability distribution. Okay, so that's where it comes from. You get I'm gonna have to erase all this. It's bell-shaped. The first thing about the normal probability distribution is that it is a bell-shaped distribution or a bell-shaped graph. Okay. Now, a second thing that we really care about with the normal probability distribution, the second thing is that it is symmetrical about the center, which is the mean. Okay. So again, let's draw this back in. My graphs are not going to be perfectly symmetrical, sorry. Okay, but in the middle, we have the mean. Okay, this is the mean in the middle, roughly. In the mean, we have the middle. And then this is symmetrical. Okay, at least it's supposed to be symmetrical, right? In your book, it's symmetrical. So this area, right, this is supposed to be the same as this area. Okay. So it's symmetrical, right? What's symmetrical mean? Have a piece of paper, fold it in half. This side is equal to this side, right? It's supposed to be a perfect copy, a perfect reflection. So if you divide this down the middle, which is what we're supposed to be doing, right? This will be equal to this, okay? So we have a bell-shaped curve. It's symmetrical about the mean or about the center, okay? That's the second characteristic of the normal probability distribution. Okay, the third, once I draw this back in here, is that area, okay, and this is an important one for when it comes to calculating probabilities, okay, that area under the curve, okay, the area under the curve is equal or identical to probability. Okay, the area under the curve from here to here, the area under this curve. So the line on the top, the bell, right? The bell shape, the total area under this curve is the same as probability. Okay, it's equal to it. Which also means that the total area under the curve is 1. Remember, so this is area under the curve going from here at the negative at a low point here at a positive point, okay? The total area under this curve is not, it's equal to probability. So the total area under this curve is the same thing as probability because this is a probability distribution. And then the total area under the curve is 1 or 100%. Okay. Just think about it like this. Okay. Just if you want to try to imagine something like this, imagine you're flipping a coin for a probability distribution, right? What's a probability distribution? Just the combination of all the potential values a variable could take on and the likelihood of it occurring. That's a probability distribution. This is one of them. Okay. Well, what are the potential values that flipping a coin could take on? It could take on heads. It could take on tails. Heads, tails. What's the probability of heads? 0.5. What's the probability of tails? 0.5. So if you add it all up, heads and tails, 0.5 plus 0.5 is 1 or 100%. So the total area underneath this curve adds up to 1. And yes, I do mean area, the same way that you could have, say a 2-foot rug by a 3-foot rug. That 2 by 3 works out, 2 times 3, that's 6. That's 6 square feet. Well, here I'm referring to the area under the curve, which breaks out to a total area of 1. And it has to add up to 1 because this is nothing more than probability. So area and probability are the same. Okay? So total area under the curve is equal to 1. The reason why that matters so much, let's just pretend that this is 100 right here. Okay? Let's say that on average, IBM stock is $100. What happens? What if we want to know the probability? Let's just suppose for a second. Let's say we want to know the probability that IBM stock finishes the day between 110 and $120. Okay. In other words, I want to know if IBM stock finishes the day between 110 and 120. Okay. Well, 110, 120. In other words, I want to find out the probability that IBM stock finishes the day between 110 and 120. In other words, I want to find out the probability of this interval occurring. Well, how would I find out the probability of this interval occurring? Hold on a second. Wait a minute. I know. Probability is the same thing as area under the curve. So if I wanted to find out the probability of IBM stock finishing the day between 110 and 120, then all I would do, if I want to find this interval, I need to find the area under the curve of that interval. So in other words, if I can find this black shaded region, if I can find that area, then I already know from the normal probability distribution, if I can find that area, well, area under the curve is identical to probability. So if I could find this shaded region, that shaded region's area will be the probability of something happening between 110 and 120. In other words, I will be able to scientifically calculate the probability of IBM stock finishing the day between 110 and $120 if I can find the area under the curve right here. That's a big deal. That's a very big deal. Okay. Fourth, this entire curve, the normal probability distribution, it is asymptotic. It's asymptotic between negative infinity and positive infinity. Okay, so this is negative, this tail, this endpoint is negative infinity, and this tail, or this endpoint, is positive infinity. Asymptotic just means that it keeps going towards the axis. It goes towards the axis, but never actually touches it. It just keeps on going. It never actually intersects. Okay. Keeps on going, but it never actually intersects. That is what asymptotic means. Okay. It's asymptotic between negative infinity and positive infinity. So this bell shape keeps getting closer and closer and closer and closer, but it never actually touches. Okay, never actually touches. And then finally, finally, these are four characteristics of the normal probability distribution. It's bell-shaped, it's asymptotic, it's symmetrical about the mean, the area under the curve is identical to probability, and that area under the curve is 1. There's a fifth one. It is only for the standard normal probability distribution, which is that the mean is 0 and a standard deviation of is 1. Okay. So in other words, for the standard normal probability distribution, the mean is 0. This would become 0. So in other words, the center of the graph, the center of the distribution becomes 0. And a standard deviation would be 1. This would be -1. This would be +1. Okay. So in other words, if you said, oh, it's 1 standard deviation away from the mean, then you would say, oh, okay, that's between 1 and -1. Or if you said it's 2 standard deviations from the mean, then you would say -2 and 2, right? So like to go back to the empirical rule, right? Part 2 of the empirical rule, 95% of all observations are within plus minus 2 standard deviations of the mean. Well, for the standard normal probability distribution, if 1 standard deviation is 1, then that means 2 standard deviations would be 2. 95% of observations would be between -2 and +2, right? So this would be 95% of everything that could occur. That's only for the standard normal probability distribution. We're going to come back to that in a couple seconds, okay? But just for our introduction to the normal probability distribution, okay? The normal is bell-shaped, symmetrical about the mean, the center, right? The mean. The area under the curve is identical, equal to probability. The total area under the curve is 1. Why? Well, if area and probability is the same here, well, all probability everywhere, all probability has to add up to 1. So that means that the total area has to add up to 1. And then it's asymptotic between negative infinity and positive infinity. Okay. If we want to add in one more condition for the standard normal probability distribution, we have a mean of 0 and a standard deviation of 1. Okay. So now we need to get on to seeing how or why this is so important. Okay. In other words, if the normal probability distribution is just one probability distribution of all the different kinds that exist, why does it matter, right? I mean, sure, English is a nice language, it's great, okay? It's not particularly pretty, really. But why is that the one that everyone uses? Why is it so, efficient, quote unquote, to have one language? Okay. In other words, why do people convert, whatever language they're speaking, usually into English when you're having international communication? Okay. Well, the answer is because usually if, someone from Japan is speaking to someone from Brazil, it gets converted into English because that's a standardized global medium that everybody pretty much understands, right? People have a working knowledge of it. Everybody kind of gets what's going on, more or less, right? I don't mean to generalize too much, but once you get into English, everybody kind of has a working knowledge of it, at least nowadays. And so that is a quick way of making comparisons across international boundaries. It's the same reason why the entire world, other than the United States, uses the metric system, because a person in Japan is the same height as a person in Brazil. If you say, "Oh, it's 2 meters tall," instantly everybody knows exactly what you're talking about, right? So it's just the United States who continues to avoid the metric system. But what it does is it gives us this nice international comparison that everybody can quickly reference against. In statistics, there are an infinite number of probability distributions out there, but everybody uses the normal probability distribution, and specifically the standard normal probability distribution, because that creates a quick international reference point to understand what's going on, whether you're talking about the growth rate of bananas, the strength of a heartbeat, the amount of defective tinfoil rolling off the Frito-Lay assembly line, or the price of IBM stock. Okay, it doesn't matter what the variable is, whatever you're looking at, right? The standard normal probability distribution is applicable to all of it. You can convert all of those probability distributions into the normal probability, and specifically the standard normal probability. So that's why it's so important. That's why it's used everywhere, okay, throughout all statistics. Okay. So how do we convert it, right? In a sense, like what's our translator? How do we translate into the English of statistics, right? In other words, what is the universal language of statistics? Okay. So, for example, if I told you that, let's say, so I do a lot of running. Okay. I ran again this morning. Let's say that I told you that I ran an 8-minute mile this morning. You'd say, "Oh, okay, all right, that's maybe pretty good time, fast, maybe not too fast, whatever." But how does that compare to what you do normally? How does that compare, right? So, in other words, if I usually run 4 miles at a 6-minute pace, and then this morning I did 4 miles at 8 minutes, you might go, "Oh, Rafferty, why did you go so slow today?" On the other hand, if I normally run 4 miles at a 10-minute pace, then you say, "Oh wow, you were flying today. You normally do 10, you were only doing 8. That's pretty good." Or if I normally run, 4 miles at a 7:55 pace, you might say, "All right, like a little slow, a couple seconds off, but not too crazy," right? So in other words, to get all that information, whether I was going really fast or really slow or right about what's normal, I needed to give you more context. I had to give you additional information for you to decide whether or not I was going fast, slow, normalish. Okay. In statistics, we avoid having to do all of that simply by converting into the standard normal probability distribution. Okay. Every single observation, everything in the entire world, literally in the entire world, can be shown, but you can understand how typical or atypical, how common or uncommon, how normal or how weird something is. You can understand all of that, every single thing in the world, simply by looking at its z-score. Okay, its z-value. That's what a z-score is. You've probably heard of these before. You should have, but you may not have understood exactly what they are. Okay, a z-score is nothing more than how normal or how weird, how common or uncommon a specific observation is in relation to what's considered normal. Okay. So let's just, very quickly, let's say that an average man is 5 feet 10 inches tall. Okay. Let's just, assume that, right? Okay. Well, I'm 6 foot 2. I am considered tall for the, male height, but I'm not crazy tall. People don't go like, "Oh wow, he's huge," right? And you go, "Ah, he's tall. He's not that tall, but he's taller," right? On the other hand, if you had Shaquille O'Neal, right, people would go, "Oh, he's huge," right? He's huge. He's a basketball player. He's a gigantic basketball player. So he would have a very large positive Z score. He's considered way above what's normal. Whereas I have a positive Z score. I am above what's considered normal, but I'm not, way out there. I'm not super big compared to everyone. My Z score is positive, but not too positive. Okay. At the same time, somebody who's 5'8", they're shorter than what's considered normal, right? 5'10", if that's normal, 5'8" is below average, but it's not, it very below average. It's not, they go like, oh, shorter, but it's pretty much average, right? Okay. So that would be a negative Z score, but it wouldn't be very big. It'd be, it's negative means that it's below the norm. That observation happens to be below what's considered normal, but it wouldn't be something large to be like, whoa, look, that is a shorter person. Okay. It wouldn't be a cause for concern if you were talking about, height development. On the other hand, if you found somebody who's maybe a foot shorter than what's considered normal, that would probably be something that a doctor would want to look into, right? The doctor would say, okay, this person is below average height, but fairly, it's way, it is noticeably below what's considered average. And so therefore we want to take more of a look at it. Okay. And at that point, the doctor would do what the doctors do. Okay. But that would be a Z score that is bigger, would be negative and noticeably so. It wouldn't be like for somebody who's, 5'9" or something, right? Same thing with stock prices. If the average stock price is $100, and currently IBM is selling for 105 or 95, people probably wouldn't take much notice. Like, all right, it's above what's normal, it's below what's normal, but not too much. But if suddenly the stock price was $2 or $302, you would say, whoa, that's way out there, or whoa, that's way down there. And then you should probably run more tests to find out why that is, why there's such volatility or swings in the stock price. Okay. That's the whole point of Z scores. Z scores give you information of instantly about how common or uncommon something is. So what's a Z score? A Z score is simply the number of standard deviations that an observation is from the mean. It's the number of standard deviations that an observation is away from the mean. Okay. So in other words, if you have a standard deviation of 0.5, you're above the mean, you're above the average, but not excessively so. If you have a z-score of negative 0.5, you're below what's considered average, but not really excessively so. If you have a z-score of, 4, then that means you are 4 standard deviations above what's considered normal, and that would be way above the mean. Whereas if you had a z-score of negative 4, that would be considered way below the mean, way below the average, and maybe that should be looked at for whatever reason, whether it's stock prices or height, okay, or anything else in between. So a z-score, okay, a z-score is simply the number of standard deviations. That's what it is. Every time you get a z-score, let's say your z-score is 2.47. 2.47 is the number of standard deviations that observation is from the mean. So a z-score of 2.47 means that you are 2.47 standard deviations above what's normal. Okay? So, how do we get z-scores? Pretty easy, really. A z-score is nothing more than x minus mu divided by sigma. X minus mu divided by sigma. Okay. So remember, mu is the arithmetic mean. We calculated that in chapter 3. Sigma is the population standard deviation. Okay. It is a measure of dispersion. It's how far away most of the data is from the center, right? Mu tells us the center of where our data is located. Sigma tells us how far away is the rest of the data from the center, okay? And then X is the value of the observation. It's the value of the observation, okay? So let's do a simple one, right? Let's say that we want to know, okay, we want to know what is the z-score of an IBM stock price of $110 if the average is 100 and the standard deviation is $7. Okay. So in other words, what's the z-score of an IBM stock price, of an IBM stock price of $100 if mu is $100 and sigma is 7? So in other words, we have 100 in the middle for now. And our sigma is $7. How would I get the z-score? Okay, well, right now I have 100 for my average, and I have 110. I want to know the z-score. Okay, well, x could be 110, right? I said that x is the value of the observation. So the value of the observation is 110. I look out and I see today, hey, IBM stock price, 110. Okay. And then I want to know, would that be a common thing or an uncommon thing, right? So in other words, based upon an average of 100 and a standard deviation of $7, if I go and look out, and I say, hey, I wonder if there is a good chance or if it would be probable or improbable for the stock price of IBM to go to $110, right? So I want to know what the odds of that would be. Okay. So here's how I could go and do that. I simply do 110 for my x minus mu, which is 100, divided by 7. X minus mu, my average was 100, and my sigma is 7. So 110 minus 100 divided by 7, this gives me 10 over 7, which comes out to be 1.43. I'm rounding up. It's 1.428. I'm rounding to 1.43. So in other words, I convert my 100, I convert that to 0, and then my 110 gets converted to 1.43. Okay. So what this is trying to tell me, okay, is that, hey, Devin, if you have a stock price that is $110 and the average is 100 with a standard deviation of 7, okay, well, would that stock price of 110 be like normal? Would it be above average? Would it be below average? Would it be way above average? Would it be way below average? We don't know. Like, what is it? So what that tells me, 1.43, 1.43 is the number of standard deviations an observation is from the mean. So in other words, this stock price right here, this stock price of 110 is exactly 1.43 standard deviations above what is normal. And now I know that, 1.43 standard deviations. Is that a lot? Is that not? Well, it's positive, and I mean it's kind of significant, but it's not like somebody who would be, 8 feet tall walking into a room of people who's 5 feet 10, right? If Shaquille O'Neal walked into a room of people who's 5 feet 10, you go, oh my goodness, look at this, right? That's way out there. Okay. That would be, 4, 5, 6, 7 standard deviations, right? For us, 1.43 for the stock price, it's not nothing, right? It's something. It's definitely positive and noticeable, but it's not something that's too exorbitant. Okay. So that is what a z-score is. A z-score is the number of observations, the number of standard deviations, excuse me, the number of standard deviations an observation is away from the mean. And it's relevant because what it does is it allows us to universalize or to understand anything that exists, whether it's IBM stock prices or if it's uh, somebody's pulse, or if it's what you can expect while running, or if it's the depreciation rate of an exchange rate, or the speed at which your phone's battery recharges itself. All of those things, anything in the world, we can convert all of those probability distributions into the normal probability distribution, specifically the standard normal probability distribution. And what that does is that gives us a universal way of looking at different comparisons, right? We can compare different observations across basically anything to say, oh, that's way above average. Oh, that's way below average. That's slightly above average. That's slightly below average. All those types of things. All of those can be had instantly. We can get them instantly simply by converting into the standard normal probability distribution and looking at z-scores. Okay, that's why it's relevant. The same way that you can understand it's time to eat lunch in Japanese, you can understand it's time to eat lunch in Portuguese, you can understand it in French, in German, in any of those languages. But if somebody in Korea was speaking to somebody in Brazil and they said it's time to eat lunch, they would probably get somehow towards English, right? They would probably use English in order to communicate it, right? English or French, most likely English. Well, in the same regard, you would be able to get universal comparisons of anything that exists in the world, whether it's recharging lithium ion batteries, exchange rates, stock prices, weights, uh, defective Doritos tinfoil bags, right? All of those things can be calculated. And whether this is happening a lot, if it's way above average or way below average, right? It's not happening at all. We can calculate all of that from the standard normal probability distribution because Z scores are simply telling you how likely it is that something is happening. Okay. It tells you, okay, this is way above average, this is way below average. That's the whole point of the Z score. Okay. Since now we can find out if something is way above average or way below average, this or that, now we can start calculating probabilities using the standard normal probability distribution, which is what we are going to do next.